Lesson 3, we're going to talk about pH here. So pH stands for the potential of hydrogen, and anytime today you see this P that's lowercase, you're going to take the negative log of whatever follows it. So like pH means take the negative log of the H, and that's what you see here. Theoretically, there's no limits, but we generally use 0 to 14, and it's unitless. So here's a representation of the pH scale. So you'll see 0 to 14, acidic, underneath 7, above 7, basic. It is log base 10, so each step represents a factor of 10. So 0 to 1 would be 10, 0 to 2 is 100, 0 to 3 is 1,000, and so forth. We're going to talk about calculating pH a lot today, so we're going to talk about the difference between strong and weak in terms of acids and bases. If it's strong, you'll treat it one way. If it's weak, you'll treat it another way. So the good news is strong acids and bases completely break apart, so it makes our lives easy. If we start out with 0.5 molar of HCl, we know we end up with 0.5 molar of the H, okay, and 0.5 molar of the Cl, because it all breaks apart. If we start out with 0.5 molar of NaOH, we know we end up with 0.5 molar of Na and 0.5 molar of OH, because they all completely break apart. So we're trying to calculate the solution of a 0.030 molar hydrochloric acid. So when we work with this today, calculate the pH of it. Okay, so this is our concentration of our H because it's an acid. So I'm going to take pH, which is negative log of the H, which means negative log of the 0.030 number. And when you do that, we're always going to round to 2 decimal places anytime we do pH or POH, so we'll talk about in a minute. So we get 1.52, and that's our answer. Calculate the pH of a 0.01 molar solution of calcium hydroxide. That's this, if you think about your crisscrossing, and that's a base. We know it's a strong base. When this breaks apart, we're going to get calcium, and we're going to get 2 hydroxides. And that's because there's a 1 and a 2 here, so that 2 is going to translate here. Now, when we work through this, we need to find the pH. The problem is this is OH, not H, so we have to find something called the POH first. The POH is just the negative log of the OH, okay? And when we write these square brackets today, that's talking about a concentration. So that tells you what concentration in polarity do you have of that thing. So we know we have our concentration here is actually 0.02 molar because there's 2 of it here. So 0.01 times this 2 takes us to 0.02 molar, and that's what we're going to use to plug in. So POH is negative log of the 0.02 number, which rounding to 2 decimal places, as we always want to do, is 1.67. Then there's another quick equation that we're going to use a lot, and it's pH plus POH, 14. So I can find my pH then by subtracting from 14. So if I take 14 minus 1.7, that's my pH value, which would be about 12.33. And that's our final answer here. So for this one, you would say it's 12.33. We got that by taking our POH and subtracting from 14. For the next one, calculate the pH, the POH, the H plus concentration, square brackets, and the OH concentration, again, square brackets, I'm thinking concentration. You need to be a little familiar with undoing logs here, and it's log base 10. So if I want my H concentration, I would take 10 to the negative pH to undo it. If I want my OH concentration, I would take 10 to the negative POH. That's undoing the logs. You may be familiar with that in math class. If you're not sure how to do that, just remember this equation. That's what we're going to work with. So when we actually try this here for one of these, what we're going to have to do is find our concentrations and then plug in from there. So 5.5 grams of hydrochloric acid. So we're going to set up a quick conversion to get that into moles. 36.45 grams. Use the periodic table, add up an H and a Cl. That value is going to be 0.151. And that's moles. Then we're going to divide it by our liters, which is 0.25 liters, converting that to liters. And that answer is about 0.604. Capital M for molarity, because that's our concentration. Now, that's our concentration of the H, because this is an acid that we're talking about. It's HCl. So our base, that would be OH. But what we're looking at here when we calculate this is now we have our H concentration, so we want to find H, negative log of that number, which is, when we plug it in, we're looking at a pH of about 0.21. I can find my POH, 14 minus 0.21. So that's 13.79. And then I can find my OH concentration by just undoing my POH. So 10 to the negative POH, 10 to the negative 13.79, which my final answer there then is going to be really small. It's 1.62 times 10 to the negative 13 molar. Okay, and I will be plugging that in my calculator here to get this answer. Now let's talk about the weaks. So we'll leave B and C there that you can do. But if we look at the weak acids and bases, the problem is it doesn't completely break down. It's not like all of it converts into the reactor, the products here that we see. Remember we drew that backwards arrow before saying a lot of it stays as is. So that's a problem. This K value comes into play then because we can figure out how much breaks apart the products divided by the reactants to figure out how much actually broke apart. So if our K value is greater than 1, that means our numerator is greater than our denominator. So that means more broke apart than not. If it's less than 1, we have more stayed together. Okay, and you would see that because then that means our denominator is higher than our numerator. So we're going to use this K to help us figure things out. So the equation here that we're seeing, okay, looks like this. Now what this is an ICE, initial change equilibrium table. You would see them a lot in AP Chem. We're not going to get super in depth in them. The only thing that we really care about is that these two values here end up being the same. That means that when we have our K expression, since these two are the same and these two both go on the numerator, that means we can just use the one value and square it, okay? Now we've shortened H3O plus to H plus here, and that's the only real difference. pKa, though, is the negative log of the Ka, because that just means take the negative log of whatever follows. So we're going to give this a try here. So what's the pH and the pOH of 0.01 molar of hydrofluoric acid? And we have our Ka value there. So we're going to plug into our Ka equation. So that's H concentration squared over the acid itself concentration. We're going to do some plugging in. This is our acid. This is our Ka. Okay, so we have our Ka is 1.1 times 10 to the negative 10th. We have our H is percent squared, and then we have 0.01. So when I solve for my H, just some algebra there, you're going to end up with a value that we're going to use to find our pH. So that value is 1.049 times 10 to the negative 6. Now that we have our H, our lives pretty easy. We can find our pH pretty easily by just taking negative log of this number. So when we do that in our calculator, we're going to get about 5.98. And to find our pOH, we would then take 14 minus our pH, 5.98 here. And that value is going to end up being 8.02. Okay, so the only difference is using this equation here to start us off. We go from there. The next one you would solve the same way. You get a Ka value. As soon as you see a Ka value, you should be thinking a weak acid because they're generally not given to you for a strong acid. Let's try this one though. If an ethanoic acid has a pKa of 4.74, what is its Ka? So if you want to undo the pKa, you would take 10 to the negative pK like we did with pH and pOH. So 10 to the negative 4.74. So the Ka value here then would be 1.82 times 10 to the negative 5th. We look at the next one. So if propanoic acid has a Ka of that, what's its pK? You would say pKa is equal to negative log of the Ka, which is negative log of the 1.38 times 10 to the negative 5th. Which, when we solve for that then, we would end up with, when we plug it in our calculator, about 4.86 here. So which is a stronger acid, propanoic or ethanoic, okay? So one big thing that we're going to see is the lower the pKa, the stronger the acid. So to solve this question, I'm going to look at the pKa of propanoic versus ethanoic. So 4.74 versus 4.86, okay? So the lower of the two is the stronger acid. So since the 4.74 is lower, I would say ethanoic is stronger. And you would say because it has a lower pKa. All right, weak bases are pretty much treated the same way. What you're going to notice is the same kind of table that shows you that these two values afterwards end up being the same, which allows us just to simplify this. So we have Kb is our hydroxide concentration squared over our concentration of the base at the beginning. Okay, and then the same thing applies. The lower the pKb, the stronger the base. Okay, So when we look at this, we've got a pKb, we want to find its Kb. So I'm looking at these and I'm solving for pKb in this case, or Kb. I take 10 to the negative pKb. It's 10 to the negative 4.75, which then when I solve that, I get 1.78 times 10 to the negative fifth. If this is the Kb, what's its pKb? So pKb is negative log of that number. I solve that, I get 3.36. So then which is the stronger base? I'm comparing the two pKb's, that number and this number. 3.36 is definitely lower. So I would choose methylamine. My reasoning would be is it has a lower pKb. All right, so there's a bunch of problems in your practice packet that we're going to be looking through and trying to work through, but these are generally some approaches that you'll use. When you get to some problems with the pKb, you can also have to set up this equation, solve for something like hydroxide concentration to find the pOH and things like that.